Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good morning. So today I'm going to explain or share the knowledge on how to run the electrochemical performance of the material if you are studying, for example, supercapacitor. First of all, it is divided into 3 electrode system measurement and also 2 electrode system measurement. So in this video, we're going to discuss on the 3 electrode system measurement. So what actually we're going to run and what actually we're going to discuss. So basically, for the electrochemical performance of nickel, bimetallic or whatever, what we call that, whatever material you have, the electrochemical performance, for example, the conducting polymer, carbon-based material, metal oxide, whatever is it, you must do 3 electrode system first, then you also can study the 2 electrode system. Sometimes the journal only reported up to 2 electrode system, sometimes they report until 3 electrode system, sometimes they report both 2 electrode and 3 electrode. So we're going to do full 2 and 3 electrode, but in this video I'm going to share to you on how actually we want to run the electrochemical test for 3 electrode system first. So basically in 3 electrode system they have cyclic photometry. Okay, you must run first cyclic photometry to know the potential window. You want to know actually your material can form the CV curve at what potential window. If your material is positive electrode, you can run from 0 to positive 1 or positive 2 and to see the CV curve. If your material is negative electrode, for example, is carbon based, you can run from 0 to negative 1 or even negative 2 to observe the CV curve. So basically it's all about try and error first. We want to know exactly at what potential window the electrochemical test can be observed. Okay, first of all is cyclic photometry, and then after you have done the cyclic photometry, you can done the cyclic photometry at different scan rate. So for 3 electrode system, cyclic photometry at different scan rate is important because you want to know when you increasing the scan rate, is it the CV curve can be retained or not. It is important step, so you should run your CV curve at different scan rate. Okay, then after you finish with cyclic photometry, you're done. So now you're going to do the analysis of GCD, Galvanostatic Charge Discharge. For galvanostatic charge discharge, you should already know the potential window from the CV. For example, you run from 0 to 0.7 volt. So from the GCD, you should focus and fix the potential to 0.7. It should achieve that potential. And then from the GCD, you want to get the, what we call that, the discharging time. From that, you can actually calculate the same. You also can calculate the specific capacity. Using CV also we can calculate. Using GCD also we can calculate the specific capacity or the specific capacitance, depend on your type of material. If you're battery type material, you calculate specific capacity. If you are pseudo capacitor or EDLC, you can calculate specific capacitance. Okay, so next after that, what you need to do is for the GCD, you need to run at different current density. For example, 1 ampere per gram, 2 ampere per gram, 3 ampere per gram, 5 ampere per gram. At least 5 different current density for the GCD. Okay, after you finish, you actually successfully get the GCD. So what you need to do is you run the EIS for 3 electrode system. For the EIS, for supercapacitor, you can observe the ESR. So you can see actually the ESR, and then you can calculate, you can observe the RCT, and you can also observe the Waback line. So the ESR at the beginning, as you can see from the graph here, at the beginning, this is the ESR. And the semicircle, the diameter of semicircle, we call that the charge transfer resistance, RCT. And the straight line is a Waback line that indicates electron diffusion. the shorter the wabak line is, the better. More straight the wabak line is also better for faster electron diffusion. Okay, let's go into detail, a little bit detail on how to run the cyclic photometry, GCD and EIS for 3 electrode system in what? In electrochemical test for supercapacitor. Okay, first let's go to CV. Okay, CV first, you want to run the 3 electrode system. So first you run a big scan rate. So actually like you can also run from -2 to 2 if you didn't know your material. What is it? Is it battery type? Is it EDLC? Is it pseudo? You don't know. Just run a big potential and you just can cut at where you can see at where there is no hydrogen evolution or also oxygen evolution. If you observe a straight line, if you can see from the graph here, this graph is good because there is no hydrogen and also oxygen evolution. So that's why we fix the potential from 0 to 1. So you need to try at big potential, then you narrow down the potential window. So what you need to put from the CV if you are using Nova software, so you just click here, the CV staircase, just input the start potential. Normally we put 0 or 0.0002. Next, the upper voltage is 1. So until what potential window you want to set. If until 2, just upper voltage is 2. The lower voltage is 0 because you want to end with 0. Stop potential also 0 because you want to end the potential at 0. Okay, number of scan depend on you. If the first trial without different what we call that different scan rate, just run 2. No need to run 10 cycle or whatever. Okay, for the scan rate, normally people study 5 millivolt per second, 10 millivolt per second. You can choose for the first CV to know the potential window. No need to run at low scan rate because it's very long. So you don't want your measurement to be very long. So I suggest you can use 5 millivolt per second. Okay, next, the rest is nothing. Okay, then this is nothing also. Just click run after that. Okay, you can click run button so you can get your result like this. Depend on your material. If EDLC, you can get a rectangular, almost rectangular. Pseudo is a distorted rectangular. Maybe you can see a leaf shape. This is like a leaf shape. So this is a pseudo capacitor. So if battery type, you can observe clearly a redox peak where it's anodic and also cathodic peaks. So first observe the shape is very important. Secondly, know the potential window. Okay, enough with CV, that's all. So next, after you know that, you must set up the experiment for different scan rate because you want to study cyclic photometry at different scan rate. You want to observe the shape. Is it the shape shifted to the right, shifted to the left? What happened? You must understand and read some journal and explain if the shifting happened, what happened to the material. So basically, if there is not much of shift, means that the material is good because electrolyte can, even at high scan rate, what happened is the electrolyte can move to all active site. But normally at different scan rate, you also can observe a trend. At low scan rate, the capacitance will be high compared to high scan rate because at high scan rate, the electron or the electrolyte ions doesn't have enough time to travel to all active site of the material because you scan it very fast. Okay. So what you need to do from the software here, just click here, repeat for multiple value and click CV staircase. So here from start potential, just click 0, upper voltage 1, lower voltage 0, stop potential 0. It's the same, almost the same with the individual CV curve. So the only difference is the number of repetition. So number of scan is 2 because we only take the second scan for every scan rate. Okay, the scan rate, for example, 5 millivolt per second for number 1. Okay, next, click number 2 is changed to 10 millivolt per second. So we repeat for 6 times. It depends. You want to repeat increasing 5 or increasing 10. So you can, in my case, I increase at 5, 10, 15, 20, 25, 30 millivolt per second. Why you not do until 100 millivolt per second? Because the CV shape does not retain. So sometimes If the material is not suitable, you can just reduce the number of scan rate. No need to scan very large scan rate. So in the beginning, you also can set from 5 to maybe 200 millivolt per second. Then you can choose the graph. If your graph is good until 50 millivolt per second, you just leave it like that. Okay, so for CV procedure, here the important things to know is for the repeat for multiple value here. If you click here I set the number of repetition is 6. You can click more here, just click more, and here you can adjust. For example, here I click 5, 10, 15, 20, 25, and 30. You can actually add, for example, you want to add 0.035. I want to add more, 0.05, 0.01, until 100, 0.02. It's okay. It doesn't matter. Just click enter, then enter. Until you satisfy, you want to vary at what scan rate, doesn't matter. Okay, so for papers or journal, minimum is 6. So you can increase 5, 10, 15, 20, 25, 30, or 10, 20, 30, 40, 50, 60. It depend on you. Depend on your creativity. It's okay. And depend on your CV curve, if it can retain the shape or not. If not, it's quite difficult to discuss in the papers. Okay, so just click run after that. It's quite simple for CV. Okay, then after that we're going to run the GCD. So it's quite a little bit difficult for GCD. Sometimes some problem happen. For example, your GCD curve, the triangle or the distorted triangle, cannot achieve the desired potential window. Sometimes your potential window you scan from 0 to 1, they only can achieve 0 to 0.7 only. That's very bad lah. You must increase the current density, because the higher the current density, the ability to achieve that potential window is higher. So what happened? Okay, we go deeply how to run it. Okay, so you just click one by one. Innova, nothing is hurt you. Just click one by one and understand. So first, okay, click here, number 1, the message number 1. Okay, you input the value of current. Value of current, how you get the value of current? So for example, you want to study 1 ampere per gram. Okay, 1 ampere per gram. So what happened is your current should be ampere per gram. So you want to get current, so you should divide your mass. So for example, 1 ampere per gram. So you already know your mass. For example, your mass is 0.0165. Okay, you want to get current, you just divide by 1. So now my mass is 0.0165 equal to my current 0.0165. Because of what? It is in 1 ampere per gram. If 2 ampere per gram, your mass should be times 2. If 10 ampere per gram, times 10. It's divide. It looks like that. Okay, so in this case, because it is 1 ampere per gram, so it should same with your mass. If your mass is 0.1 gram, it should be 0.1 here. Okay, next, this is the negative, only including the negative value. Okay, this is your potential window. You want to scan until what? If you want to scan until 1, just change the value to 1. Okay, next, you want to cut off the voltage at what? We cut off normally at 0. Okay, this is nothing. Okay, next, the apply will show the same. Input the amount of current. Okay, last but not least, here the repeat and times. So normally we repeat the GCD also second times. We choose the second graph, not the first graph. Okay, so at the repeat and times, you click here, just set current. Okay, input the amount of current, the same. Okay, so for record signal, normally you put the higher value. Normally it's not achieved the 100 second. If achieved, you just put more. There's nothing so much important here. Just put more, because normally it's discharge less than 600. If your sample is very good, it's have a longer discharging time, you can increase the time to 1000 or 2000. Okay, then this is the cutoff voltage. If you are scan until 1, put here 1. Okay, so the discharging current at negative, and also the record signal here, it should stop at 0. then you just run. If you run the sample, you can get the graph like this. If like this is the battery type, you can get a plateau here. Okay, last but not least, if your CV is okay, GCD is okay, you also run GCD at different current density. And last but not least, what you want to do is you run the EIS. So EIS quite simple. So this is what I call that the OCP unit. You need to run your bare substrate with your electrolyte and put into a 3-electrode system, and you find the OCP, the potential, operating potential. What is it? So in this case, negative 0.24 volt, because we are using AgCl. Okay, next, so for Fra measurement, you just include the scan rate. Normally we are using 100,000. In this case it's only 10,000. You also can increase to 100,000. Okay, next is the last frequency, should be 0.101. It depends on your sample. Okay, then the amplitude is also important. Either you want to scan 5 millivolt per second, 5 millivolt, or 10 millivolt, the amplitude. So the amplitude, to see if there is no amplitude, means there is no semicircle. You must add the amplitude into it. Okay, then nothing, just click run. So you can get the Nyquist plot, both plot, and also both phase. So the important thing here, the Nyquist plot. So here is what you should do for the electrochemical performance, basic thing you should do. So later I will explain on how to discuss it. I think that's all. Okay, bye.